a network of n nodes labeled 1 to n is provided, along with a list of travel times for directed edges, represented as times. So this equation right here. And you don't have to be scared about this. We will see some examples that will make this simpler. Where x1, x at I is the source node, y at I is the target node or destination node, and ti is the delay time from the source node to the target node. So the travel time, the time it takes for information to go from x to y, is represented by t. Considering we have a starting node k, so one of these nodes, right, denoted by k, we have to determine the minimum time required for all the remaining n-1 nodes to receive the signal. Return -1 if that's not possible for all n-1 nodes to receive the signal. Okay. Now here's some examples. Should help things make things clear. So this is a source of 2, destination of 1, and travel time of 1. Source of 3, destination of 2, travel time of 1, and so on and so forth. Starting node of 3, so from 3, they're asking the minimum time it will take to move from 3 to every single node. And so we have these represented, these input times represented by this graph. So they constructed this graph from these input times. There are 4 nodes, as you can see, n equals 4, so 4 nodes. And once again, we're starting from node 3. And now the minimum time it takes from 3 to all other nodes would be 2, right? Because 3 to 2 is going to take 1, as then denoted here and in this diagram. 3 to 4 is going to take 2, and 3 to 1 is going to take 1. So even if you're trying to get to 1 from 3, it's going to be 1 plus 1. Okay? Hope that's clear. Then let's look at this example. So this is an orphan node, right? You can see that the nodes always go from 1 to n. So even if you see that 4 isn't present in this array, 4 is not present in this array, despite that, it exists, right? It just means it's orphaned. We don't have travel information. So we return -1 because there's no way to reach every single node in here. Okay? Because they want to start from node 1, right? There's no way to travel from 1 to 4, so just return -1. And then this one is a straightforward case. Actually, not so straightforward because it only moves in one direction, right? It's a directed graph. So from 1 to 2. However, I want to start from 2 and to reach 1, and there's no way to do that. So we're going to return -1 as well. So yeah, worth noting. Now for the solution, I don't know why they call it Ahmed here. I think it's probably someone that works at Educative that hasn't taken it out. We use Dijkstra's algorithm, which is a popular pathfinding algorithm for finding the shortest path between nodes in a graph. And so it's ideal for this situation. Now there's all this text here, right? But I tend to like to use the diagram and just walk through the code. So let's do it. Let's do just that. Or let me see. So we're going to use an adjacency dictionary, right? That's what we're going to need. And we define that, okay, let me start from there. We define that here. So this is the function that does everything, right? That solves this problem for us. Okay, not too bad. Not too bad. So we're passing in a couple of things, the times in an array. So an array of numbers, like 3-number array. And n, the number of nodes, total number of nodes in the graph. And k, the starting node for the graph, where we want to start from. So we have these in here, right? Now this is our adjacency map. This is what we're going to use to construct our graph, okay? Pardon me. Now the source node will be used as a key, and the value is a list of tuples that have the destination node and time for the signal to travel from the source to the destination node. And that's what's being constructed here. So we're iterating through all the times over here in this branch. We're getting the source. Remember, the source is the first thing, the destination is the second item, and the time of travel is the third item. So if we've not seen this before, right, then we just initialize it with the value to be an empty array, but the key is the source, right, that we pulled here. Otherwise, if we, I mean, once we've done that, then we're ready to push for that source its destination and the travel time for it, as you can see here. So that's what we've done here. We've done that part. Now we're going to use a priority queue with time initialized to 0 and starting node k as a tuple. Okay, and that's what we're doing here. right? We initialize the priority queue, right? This is just a type annotation, so it's still type JavaScript, even though it's just typed, but it helps catch bugs and stuff. It's actually initialized to an empty array, and then here is where I do the work, right? Where I put in the starting node k and a time of 0, because the time it takes to get to the starting point is 0. So I'm gonna initialize the priority queue with that. And then the priority queue ensures that the node with the minimum time is retrieved in each iteration. Okay, take note of that. We're going to iterate over the priority queue to traverse the nodes in a network. If the node is not visited, the time of the retrieved node is compared to the current delay and updated accordingly. And now, so we're going to keep track of the nodes that we've seen before, and we're going to use a set for that. Then this delay is what we're going to use it for storing the delay time or travel time to get to the node. So this is where all the magic happens. Similar to tuple sorts in a number of ways, but our priority queue, as long as there's something in the priority queue, remember we seeded it with one thing, but as long as there's something in the priority queue, we're gonna maintain the heap property, right? So maintain we're not using a heap, right? A minimum heap or maximum heap, but we're kind of using it like one. So we're sorting to make sure the earliest thing, the thing with the shortest travel time, is always in front. And then we're going to get the first thing out of it. So the smallest thing, the thing with the smallest travel time, we're going to pop it off. So it's going to be a node represented by an integer number and the time, the travel time to get there. And now if we've seen this before, right, if it's in the set, we're just going to skip it. Okay. I think at this point, this text explanation is breaking down. So the neighbors of the retrieved node are found using the adjacency dictionary and are added to the queue with the times updated by adding the delay time from the retrieved node. Okay. Finally, if all the network nodes have been visited, we will return the computed time. Otherwise, the -1 will be returned. Okay, so let's just use this diagram and take it from the top. How about that? So we have these. N is 4, K is 3. So we're starting from 3. Reconstruct this graph. So this is the adjacency list, right? This is how they build it from the beginning. So one has a travel time. There's nowhere, 1 doesn't go anywhere. So it's just going to be an empty list, right? In this case, 2 is going to point to 1, right? So it's going to point to 1 and a travel time of 1, right? So this is the node it's connected to. This is the travel time. And then 3 connects to 2 things. 2, it connects to 2 with the travel time of 1, and 4 with the travel time of 2. So this is the adjacency list so far. And then 4 is not connected to anything, just like 1. And so it's just going to have this empty array in here. And that's what this branch of code does for us. This one I introduced earlier. Okay, it does all that. It constructs this map for us. Okay, next, we're going to initialize our priority queue with time of 0 and k of 3 as a tuple. So the time is on the left, the node is on the right, the node ID is on the right. And we did that down here. Okay, now where we have our visited sets and our delays initialized to 0. And we use the visited set to keep track of the nodes that have already been processed. The delays variable is created to store the delay time. All right. Now, for each iteration, we're going to unshift this. We remove the node from the smallest time with the smallest time from the P queue, priority queue. In this case, there is currently only one node in the queue, which is the starting node, 0, 3. So that's what happened inside this while loop. Over here, we took out the earliest thing where we sorted it first to make sure the smallest thing is first. Then we take out the earliest thing, the thing in the front of the array. And now we're going to check if we've seen it before. Now, this is the first time we've seen it in the priority queue, so we haven't seen it before. So we're going to add it to our visited set. So now we're going to add this. This is not going to trigger in this case because visited is still an empty set. But now it's going to have 3 in there because we're seeing 3 before. And I believe that this is a useful check for cases where we have cycles in the graph, I believe, so that we can keep moving forward. Okay. So now we've not seen it before. We're going to add it to the visited sets, which is what happens here, as you can see. And then we're going to update the delay if necessary. So it's our first time seeing it. Delay is 0, time is 0. So delay is not going to change. It's still going to be 0. And then, all right. And so we have added 3 to the visited set. Updated the travel time so far. So far we've not gone anywhere. So we're still at 3. So the delay is still 0. The time to travel is still 0. So delay is still going to be 0. Next, we're going to get the neighbors for 3. And in this case, 3's neighbors are 2 and 4. 2 and 4. So that's what we're going to store in here. And now for every neighbor, we're going to push them into the priority queue. Okay, and sort them by, again, at the beginning of the loop by time. And so 2 and 4 go into the priority queue here. So there's a neighbor node, neighbor time. If it's not been seen before, right, that's an important check. If we've not seen that neighbor before, then we're gonna update the time to the for the neighbor to the neighbor time plus the time from the last thing we saw in the priority queue. Use that as a new time and push it in there, push it into the priority queue with the new time and the neighbor node. Okay, so that's what's happening. That's why this came in here. And so we go again, right? That's the end of the loop, the one iteration of the loop. So we keep the queue sorted. We push the next thing, which in this case is going to be 1 and 2. So this node over here. It's the next thing we're evaluating. And then we check if we've seen it before. Have we seen it before? Nope. Nope, we haven't. So it's going to come in here. We're going to mark it as visited. Only that this time delay is actually going to change for once. So delay is going to take up what was the time for 2 in this case. So it's going to be updated to 1. All right. And then we get the neighbors for what we're looking at, the current thing we're looking at, which is 2. Okay. And that's going to give us 1 and 1. We're going to put it in a priority queue. And not just toss it in the priority queue, but first of all, add the delay. Okay. So we're going to update the time so far. So it's going to be 1. It's going to factor in this 1 from 3 to 2 when we're adding into the priority queue. And so that's what's going to happen here. And we keep doing this. We just keep going. And now everything just continues, just keeps going. The exact same thing in the while loop. Then finally we can get rid of the last thing in the priority queue. Okay. Once it's empty, we exit the loop. The function then compares the length of the visitor set with the number of nodes. In this case, they are equal, so the function will return the value stored in the delays variable, which is 2. And that's what happens down here. So it's going to check, oh, did we, all the things we've seen so far, is it equal to the number of nodes we said we had? And that lets us know if anything's orphaned, like in the example I shared earlier. And if that's the case, we're going to return the updated delay, because we're just updating delay. That's what we want to know in here. And if it doesn't, return -1. C'est fini. That's all there is to it. Now, time complexity, we, because of we're going to get E log n, where E is the total number of edges. N is the number of nodes in the network. Since push and pop operations in a priority queue take O log of n time. Okay? And now the space complexity is n plus E, where n is the number of nodes, E is the number of edges. And that's it. It's kind of intuitive, but a lot of graph things tend to look like this, have more than one thing in them, one variable, usually the edge and the node. You can think of nodes as vertices. But that's all there is to the problem. Like, comment, subscribe, share. Thank you for watching. See you next time.